Hot, okay. Working, very nice. Hey, Robert, can you hear me?
Yes, sir.
Thanks. Very good. And let's zoom in a bit. Okay, feel free to open the GeoGebra thingy that I sent you on Piazza. We'll use it today, but before we are diving into the color, into the tone mapping and dynamic range, homework questions, and of course all the settings just changed because I shared the screen for reasons that are beyond me. The reset, the layout just reset itself to. Okay, since questions, homework, or anything? All good? Homework one? You ready? Perfect. We are talking about the tone mapping and dynamic range, the big problems that our monitor is so limited comparing to the colors that we wanted to show, the range of color that we wanted to show. We mentioned gain and bias and gamma correction. And we wanted to speak about the dynamic range. What is the gap of the amplitude between the dimmest point versus the most illuminated point, the brightest point, the lightest points. They are all terms that are very much related. Brightness, the brightness, luminance, lightness. Sometimes you will hear them or will use them. They're not exactly the same, but pretty much close enough for our course. So easiest thing that, yeah. I'm sorry. Yes, question about homework one submission. Is a submission on GitHub? So program on GitHub, and the PDF that is a theoretical question go to Gradescope. Zoom, I just sent you a Zoom link. Did I send the wrong Zoom link? Let's send it. oh, yes, thank you. Yeah, I think that was a good comment. Thank you. That was. So we have scenes that are taken in a region that is uniformly illuminated pretty much. There is no spotlight directed to any particular pixel. The ratio of dimmest to brightest point will be roughly 1:1, not much more. You don't need dynamic range display for this type of scene. Indoor, no sunlight, no bright light that illuminates particular spot out there. Things change dramatically when you are still indoor, but the light's coming from the outside through windows. You don't see any part of the sky, you don't see any windows. None of the surfaces is very shiny, but still lights come from the outside, and now we are way beyond what our monitor can display by itself, of 1 to 1500. There is points where you see the sunlight reflecting, still indoor, way, way larger. Now we are on 5 orders of magnitude. Interesting things. We see some part indoor, but not the sky. And then the skies that are way, way more illuminated. And now the, again, energy of brightest to lowest. It's time to introduce our GeoGebra app that we're using today, that we see the green input that is like the signal or the image or me crossing one line on the image. So it will be just 1D. So the X direction is just what happened as I'm crossing the image across one such line. We'll assume that all you care, your resolution is a lot of pixels, but all in one row, if you want. That's the x-axis. And the y-axis is the intensity. And at the moment, we'll assume that intensity is just R plus G plus B. Very rough scale, like the total energy. And I'll give you, and in one of the following slides, there is a more accurate formula, but it's similar to this, just with each one comes with one multiplication. And we can think about brightness also as how many watts per minute come from 1 square meter of area if you're standing in the right direction. We can think about it as energy that is coming from this pixel. Back to our scene. Very large contrast. Contrast is the ratio, or the gap between the brightest to lowest in the outside door. Brightest peak in the image, lowest peak in the, well, in the scene, not in the image, or in the image that I took with on a film, not digitally, presumably. Now, the gaps are huge in all this dynamic range, but it doesn't mean that they don't have any details. Even in the highly illuminated region, we do see the details in the highly illuminated region, and we do, which are denoted by these peaks along this big curve. All these peaks denotes details that we want to preserve. We want to have them in the output. What's the dynamic range problem? That the contrast that our monitor is capable to show is much more limited. I'm repeating things that I already said, but we didn't have the GeoGebra app, and it's no harm in repeating. Here is, in my monitor, that would be the lowest intensity that I can assign to, unless it's completely dark. That's the lowest intensity. That's the highest intensity that I can assign to the pixel. And between them, the values that I can assign to these pixels are in the intensity are only between 0 and 255 for standard monitors. But you just now, in this image, I just picked 6 of them, 1, 2, 3, 4, 5, 6, many levels that you can pick after the discretization. But think about it as here are the discretizations that we are using because our monitor is capable of displaying only these few levels. We can assign only these few levels. So somehow I need to take this big dynamic range, 1 to 20 billion, and compress it, and hopefully while preserving all the details. Mouse, mouse, mouse. Okay, great images. You see them mostly after some modification already. Very, very strong bright light, but still details in the non-illuminated part, in the sunset. We want to know what's happening here. It's information that do appear that the camera was able to sense while keeping the very bright light. Coffee place, dark region over here, much brighter image over here, but we still, in the original image, there are details. Let's find a way to preserve them. Okay, talking about the dynamic range, how many gaps there are and what's the difference of energy between the the darkest non-black pixel versus the whitest. Just another way to think about what the dynamic range problem is. Our image in all the lengths of the intensities that you can sense at all, which all the range up to here, our image in the input can have values that will start here at 10 to the minus 6, 10 minus 5, minus 4, minus 3. But the takeaway is that here, notice that it's exponential. But 10 to the minus 6 in energy, in intensity, 10 to the 6 in energy. So every gap is multiplication by 10. Moving from here to here means I multiplied the intensity by 10, multiplied by 10. Here I have 7 levels of intensity that I can sense. My monitor can only show 2. That's my discretization of there is only 100 or so, a few hundred, many levels that you can show. Okay, and then my issue right now is let's ignore the color issue. Somehow we'll find a way to preserve the color. We don't change the color, which will be the ratios of RGB. We'll keep the ratio of RGB for every pixel the same. We are just playing now with what's the intensity of each pixel. We are going to change the intensity of each pixel to find a way to map the intensity from every point here to some point here. And of course, it should be somehow monotonic. If it's brighter in the original image in the world, it should be brighter on my monitor or just stay the same. Well, don't be brighter, but don't get any dimmer. The same, and the question is how to map one to another. And of course, what we want to ask is look at the whole dynamic range. Look at the image right now. The image as it stands right now. I'm talking about a static image. If I'll have a video I want to take, the highest point, the most intense point in maybe the shot to the lowest intensity to highest intensity, back to one image. I want to map everything here to only these scales right here. Now, what we discussed last meeting was to do some linear manipulation of the intensity. Right now I have the intensity. I want to change the intensity of every pixel. And I can just assign for every pixel the intensity in luminance luminosity of the pixel pi, pixel pi, the intensity of this pixel in the display, D for display, would be alpha. Remember how alpha is called? Alpha, intensity of the world, of the image of the very same pixel, plus beta, where alpha was the, remember the term? Multiplying the intensity by a constant. Yeah, sorry? It was the gain. You'll find it on your monitors, TV sometimes. And that was a and that was the bias. I'm not going to justify these terms. So let's try to play only with changing the gain on the bias, so that, once again, I'm pushing all this big graph into this part linearly. As a first attempt, we'll see the shorthands in a second. But as a first attempt, it's quite possibly it will work, and quite possibly it will be nice, but let's be aware of what are the details. So this function, by the way, is something like sinus, is something like 10 sinus of x over 3 plus 0.6 sinus of 10x. Nothing important in this particular function, but you see what's happening here. The first sinus is moving very slowly, but gets huge amplitudes, going up and down by a lot. The amplitude of the second sinus is much shorter. It's going up and down only by that amount, but that amount is something with our eye we can definitely sense. The gap between the lowest point and the highest point here are something that we can definitely see. The same as in this image, because we've easily seen all the details that happens here in real life when they are illuminated. We'll stand there, not try to display it with no correction. We would have seen these little gaps. But why do I think that this function is a good analogy to what you see in these scenes, is that you see that in these scenes, there is a big change of illumination. This region is much darker, luminosity much lower. This region is the luminosity brightness much higher, but it's really the changing in the luminosity altogether are changing very slowly. There are some boundaries and big region that is illuminated, that is in the dark, and then I'm moving to big regions that is highly illuminated. These changes are not very fast if they are in the dramatic. But I'm not saying that it cannot happen that they are both huge in amplitude and changing very rapidly, and in this case our algorithm just doesn't work. But it makes sense to look at algorithms that solve the question under the assumption that the huge differences, the big gaps, are not changing very fast. And on the other hand, there is a lot of details here. There is a lot of details, the trees over here, that are changing very fast, spatial frequency. How fast are these going up and down? But the difference on illumination in these frequencies are not huge. Why our eye can still notice these details over here in real life? Well, because our eye is extremely sensitive, but also we could adjust. When we are looking at this region, we really care much less. Right? Very good in looking at this region, care about the contrast, but the local contrast. what happened between this pixel and the pixel just nearby to it. As long as the pixel between them is large enough, I don't care very much if they're all illuminated very strongly or very lightly. It's much less annoying. I can still see the details with my eye. What I want is to make sure to see these details also in my monitor. Right? You remember the graph from last meeting. We had the special frequencies, black, white of stripes, and we had the intensity with respect to the special frequency. And I thought, if we want to be able to notice very fast changing between black and white, we would like to give them some energy altogether. It cannot be too small gaps. OK, so let's see first, before we're moving into a smarter algorithm, what happens to this graph if I just try to change the graph on the right. This graph over here. What did I do? I looked at the output signal. I started to change alpha, the gain, try to change beta, the bias, so that now I compressed everything from here into the region. So in this region, this will be the minimum gap, that would be the maximum gap. In general, of course, you don't see that our curve going downward, so actually I should have scaled it, so it would be twice as compressed. So our gain is actually should be about 0.1.5 to put everything here into everything here. Fine. Now we are in the right dynamic range. Why did I need the beta? I needed the beta because the lowest point over here, which is 0, I don't necessarily, or just above the lowest point, I want to map it into still the minimum value that I can show. So the alpha by itself is not enough. I want to also assume what is a minimum value that you can see something. But now what's the discretization causes us? The red curve is what happens after the discretization of this curve. You still have very minor details, very small details that you can see on the original graph, but that's not how your monitor works. You have to assign for each and every pixel here. Let's zoom in. In our new graph, we have to assign a value that will be either this or this or this. We are discretizing. You only have 6 levels, 100 levels to assign to your pixels in your display. So the fact that after the alpha beta, in the smooth curve, we can still see some difference after the mapping, it doesn't imply sure there is a bit more energy here, so you need to turn on or turn off the pixel. And I don't talk at all about how many pixels I have. I assume that I have tons and tons of pixels, just that I have very few values to assign to each individual pixels. Make sense? So that's a problem if I just do alpha beta rescaling. This compression, sometimes called rescaling of the values. OK, so hopefully we understand what are the dynamic range problem in this context. And by the way, I was chatting with Josh about it. It's actually homework that originally came, homework 2 originally came from his course with very minor modification, if at all. And he put it very nicely. He was mentioning that homework 1, that was different than when he was teaching it, but still shared the context. Homework 1 asked about moving pixels from place to place. Homework 2, dynamic range, we are not moving any pixel, but we are changing the value of each individual pixel, so the image looks nicer. The overall results from this, and that's what you'll implement in homework 2, is algorithm that is perfect, that can squeeze a lot of beautiful, beautiful images, and you'll see all the details with high definition tricks. You'll see a lot of details that just by linear compression you cannot see. Okay, so we can think about just scaling. We can think about one of the coordinate system, age SB, age SV, LAB, and so on. There is lots and lots of other color coordinate systems that what's common to all of them is that you have one parameter that is a color that we don't change, and there are other parameters like intensity that we do change per each color. It might be called intensity, it might be called lightness. They're all related to each other. Okay, and big goal, let's keep the contrast between a pixel and its environment if we want it to be a detail that we preserved. The contrast between a pixel and its neighborhood. It's the contrast that creates the whole story is in the contrast. The proof why it's the contrast that matters so much, a relationship between an object and its neighborhood. Intensity that our camera sensed when we read the RGB values from the camera, high definition RGB, but in the RGB camera of the box, working. The lights are on in this car. Why doesn't it look to us like they are working? Well, it doesn't look like the signs are on because the contrast is much, much stronger. Contrast to the body of the car. The same image when the contrast is black, we realize the light's coming over obviously, right? So once again, just to convince you that it's really the ratio between a value and its nearby environment. That's what we want to preserve when we do the compression. Quite cute. And the other thing that we want to keep in mind is that we have a free license to cheat completely. There is a way we understand, we conceive the image, and it doesn't need to be at all identical to the values or ratio or anything that is in the original image. You have a free license to cheat as long as it looks good and it looks the same when you're done. Right? So an image with idea of the pool table with some background. I can turn off the light, but it's not that long. What's the slide try to show is that had I tried to be accurate to the RGB values that I assigned, then because that I want to keep, well, I'm showing you an image with standard RGB, that's not high-D projector, but if this image, it looks, the balls are shiny with specular light, specular spots, the background is green but dark, but you can see the texture. Had you tried to show this image when you try to be reliable, not to cheat, the whole thing would look very dim. You have to decrease the overall intensity, otherwise the spots of the balls would look, the spots on the ball would screw the intensity altogether, and that's why the rest of the table would look extremely dark otherwise. So this image was produced by lots of cheating. And that's fine. So operations that we can do, just an example, is we look at the lightness, luminosity of each individual pixel, and linear operations like we did over here is multiplied the luminosity like by some factor. Say I want to compress it, so it would be divided by 10, and you can add something to it. And alpha, beta, and gamma correction are all done on each pixel individually. You have the sliders, And in your program, you have the potentiometers on your or potentiometers on your TV monitors. And you can change their values, but it's the same operation that works on each pixel, the same constant alpha, beta, gamma per each and every pixel. Moving toward global operations, we will start to think not about the pixel, but also in contrast of its neighborhood, what's happening around this pixel, and try to pick transformations that will be good for our pixels. OK, let's try to increase it a bit. So said we want to get the intensity of the pixel, and all the manipulation in this homework will be in the level of intensity. Now, you can use different coordinate system, not RGB, but something else, but it's not needed. It's not really needed. All of them squeeze the color outside and try to do better job, and you'll find controversial about is this what's better to which application, but for homework 2, here is what you need to do. And that's, by the way, what the original papers pretty much suggested, the algorithms that we are going to follow today. So the luminosity at the world would be at a pixel p would be assigned by, look at the RGB value of p multiplied by 20. So RGB is between 0 and 1. Multiply the G by 40. Multiply the blue at this pixel by 1. Why? Because blue has much less energy in it. This aspect, blue matters much less than red matters. Sum them all up, divide by 61. Why? Because it works. Don't worry about why this is a correct formula. Physics, eyes, and again, perception, how we understand the different colors. This will be the luminosity, the intensity of this pixel when you read it, when you get it from the input. Now, how are you going to do the tone correction using this value? So you have the input value, LW, which I doubt that you can see, maybe. Readable at the end of the room? I guess, yeah, it's fine. So I know what is the luminosity of the world at this point. I'm going to change the luminosity of the world at this particular point. Every pixel has its own intensity. And I'll compute a new value, the desired luminosity, the luminosity sub D, D for the display. That's where I want the target luminosity to be. Map from the bigger graph to the small graph. How? Various ways. That's where devil is in the details. We'll discuss how to do this transformation. For example, you can multiply by alpha and adding beta, alpha smaller than 1. That would be the simplest version. And now I decided about what I want the luminosity to be in the display level. Great, but how do I keep the RGB value, the color in the, is this a red pixel, blue pixel, somewhere in between? I don't know, but I will compute the ratio of the luminosity of the desired luminosity versus input luminosity. Again, desired, D for desired or D for display. Luminosity using any of the algorithm divided by the input luminosity. And then you're just taking the red value that you got from the input image, the red value from the input image, and multiplying by this constant, L of D divided by L of W. L of D divided by L of W. That's why what I computed, L sub D. L sub W is what was a input multiplied by the same constant by red, multiplied by green, multiplied by blue. You're getting the 3 new values of this pixel. Voila, we are happy. So it's just, at this point, it's just a linear operation on each one of the colors. Everybody is good? So recap, look at a pixel in the input, from the input in the world, compute its luminosity by following this formula. RGB are between 0 and 1. We had it twice, I don't know why. Compute the ratio of the desired luminosity versus the ratio between the desired luminosity versus the input luminosity, and this individual pixel. Different pixels might have different opinions. And multiply this number by red, multiplied by green, multiplied by blue. So you don't have to use other coordinate systems, of course. OK. But even if that's all what you're doing, there is still one slight complication. Hopefully, you will not have negative feelings toward it. When I'm changing the values of light, multiplying the luminosity of the input by alpha, going the gain, or multiplied by beta, our visual system, if I multiply the intensity twice, it would look, if I'm here are 4 pixels. So moving from completely black pixel into a dark gray pixel, into a light gray pixel, into a white pixel, you'd assume that the value to create the dark would be some, or just the darkest but gray value that you can get before 0. If that's a mean value that you can still notice that the pixel is on. And then you want to move into the dark gray and look at the luminosity of 1, look at the luminosity of 2, at dark gray, luminosity of 3, of white gray, and luminosity of 4, which is total white, as bright as possible. And you ask, what are the ratios between the luminosity? If by eye it looks like they are uniformly spread between the white and the black. I think, well, maybe I just need to, by moving from here to here or here to here, I'll just ask what is delta? What will be the delta, which would be, say, L2 minus L1. So L2 is L1 plus this delta that I computed. And since they are uniformly spread, then if I'll compute L3 would be equal to L1 plus 2 delta, adding it 2 times delta. And then L4 will be L1 plus 3 times delta. It makes sense that it will change linearly, except that's not how our vision works. As far as I know, for all sensing systems, smell the same, vision the same. We want to measure things that will create the same impact. We actually need not to add the same value to the intensity, but we need to multiply it by some number. That is that if I want them to be equally spread, to give the feeling that the gaps between them in lightness is equally spread, the same gap is from here to here, the same gap is from here to here, what I should do is to start from L1, set L2, which would be 2L1, set L3, which would be 4L1, and set L4 to be 8L1. That is, arrange a gap so you multiply by some constant. If you multiply against the energy, you'll just get the feeling that you just move the same amount. Make sense? So what we are actually sensing is a log of the actual signal. So the overall recommendation is whatever you do to the intensity, always work in the log domain. Always work in the log domain. That is, from the moment that I computed the world intensity, I want to add values to it, subtract, multiply. I'm not going to add, subtract, multiply to actually this number to the LW of P. I'm going to add, subtract, multiply by log of LW of P. Add, subtract everything, but to this number. To, let's call it F world, which will be the log. What is the base of the log? You don't care. Pick 10, nothing wrong with it, or pick 2, or pick E. It's all fine, just remember what you're picking. And then I do various manipulations about it. For example, I'll compute F prime of W, which would be 3 times F display, of this W, which would be 3 times F world. Well, let's make it 1 over 3 if we are decreasing it. 1 over 3 times F of the world. That is, I'm still doing linear operation, but I'm doing all the linear operations on the log domain. Okay, subtract, add, multiply, and just here, just before you're using this constant, just before you're using this constant so you can scale the colors. By the way, all of it appears in your homework description. Just before you're about to compute this ratio, or when you decided what is LD, well, you don't know what is LD yet. You just know what is FD. Then the log of the number that you want the intensity of the display to be. So F prime of D would be the desired log of display luminosity. But hey, I want to change the RGB. The RGB you are leaving as is. You don't need to take the logs. They are perfectly happy where they are in all the operations. You will multiply the RGB all by constants, but what are all by the same constant, but this constant would be L, as we said, the scale, which is L display divided by L world. The luminosity of these two numbers, how do I compute them? Well, L world is what I got as an input, these 3 numbers. This. The result of this formula, LD would be just, so that stays in the denominator, L world. What about LD? Well, I worked with a log of, say, base 10. then LD would be 10 times 10 to the power of f prime d. Make sense? When you need this ratio, then you're remembering, oh, well, since I took the log, now I'll reverse it and look at the numbers. Cool. It doesn't change much. Just remember that at some point you need to take the log. At some number you need to go the opposite way when you want to know what is exactly this value. Okay. So since my English was so broken, I wrote what I wanted you to know, that our algorithm is governed by the idea that there is big regions that are highly illuminated, big regions that are much dimmer, and the difference between the big, highly illuminated and low dimmer region, it doesn't change much. When I'm moving along the image, here I'm in the white region. Now I'm getting into a big dark region, go to another white, another large, but it's not a lot of details in each individual region. So the spatial frequency, remember the image from last meeting with many strips of black, white, black, white. The spatial frequency of the high amplitude doesn't change very much. Once again, this image when it just appeared, I have a big region from here to here, big region from here, which is quite dim, big region from here to here, which is quite illuminated. Once again, this is one row, X is one row of your input image. Now, there are also the smaller gaps, but the difference of the amplitude is much smaller. However, they can change very fast, very high spatial frequency. Okay, just as an example, I asked ChatGPT to rephrase it with amazing work. Okay, without HDR, looks terrible. You don't see anything on the sky. You don't see anything that happens down below. Here is an image of woods on the sky. Sky is always very highly illuminated, huge value. This part of the tree is much darker. Try to do any linear transformation without using HDR algorithms that we are going to study. And the image will look, you need to look at it at the table, at the book probably. It's either completely saturated. I want to reveal the dark details over here, but to do it, I'm sacrificing all the details that happen toward the sky, or alternatively, I'm making the whole image dark. Well, it's with the interference of our projector. You cannot see anything else, but it's clear that I need some segmentation of the region. Highly illuminated, lower illuminated, and each one is treated somehow separately. Same image that we had 2 slides ago, once again, without HDR. Okay. No detail over here. You are way above what the monitor calls max intensity, so you cannot notice any details. Back with correction, everything is fantastic. All the details are here, and all the details in the less illuminated part. Once again, before, and sorry, didn't have the after. And you have a lot of nice images over here. There is some repetition of the slides. Yeah?
Just to clarify, tone mapping is the equation of the alpha and the beta?
It's an example of tone mapping. Local tone mapping or point pixel tone mapping, local operation is just operation on the pixel where I decided about one operation, and each pixel do exactly the same. The other operations that we'll do will still be addition and subtraction, but different pixels will be subtracted or added by different values. And to determine what these values are, I need to look at the nearby region to ask, what do I want to preserve? So it looks like a very vision-like high value technique, but it's not. We'll see how the math spit it out automatically without us ever worried about what are the high and what are the low region. Quick technicality. How do I know about inputs? Well, doesn't every channel get only 2 to the 8 values in our input file? Well, if you're using ppm, you have one of the header parameters tells you it's every channel is represented using 1 byte, 8 bits, or 2 bytes, 16 bits. So it's value between between 0 to 2 to the 16 minus 1. Okay, so even ppm can represent much more. And by the way, we'll give you the file parsing. So you can assume that you already read the file. But even ppm is happy to agree with high definition files, because cameras are, of course, much better. And beyond ppm, let's remind you how floats are represented in our computer. So normal float, you'll think about the number 3.14 as 0.3 times 3.14, all in base 2 actually, but I don't remember what's the number, so we'll do it in decimal, times 10 to the 1. Okay, and 3,000 would be 0.3 times 10 to the 5th. And as you know, that's an exponent. And when we write a float, normal float number, we have some part out of the 64 bits that we are using, some part of the number that keeps the, forgot the name, everybody remembers, what is not the exponent, does it have a name? The part of the number that is not the exponent, assuming that it starts with 0 point, always assume that it starts with 0 point, and so that's my number, that's the number, so I'll write it as 0.31400, and here I'll write the exponent 1. All of it just in base 2. So you have a few bits for the exponent and a few bits for the float part, I think it's called. Okay, the same will work for a format of files called HDR files, surprise, surprise, except that it has been shown that we don't need huge difference in the exponent between the channels of the same pixel. So for space saving, and because it's decided to be enough, what I did was take 32 bits. Here is the exponent. Use the last bits. The last 8 bits are the exponent of all three channels, RGB. 8 bits for the red, 8 bits for the green, 8 bits for the blue, and the rest 8 bits are the exponent. So you take RGB, multiply by 2 to whatever is written here. And what's written here could be positive or negative. Okay, so negative will just be, negative would be this number divided by 2 to the exponent. Make sense to everybody? Just a format that was developed so I will not have to spend 32 bits per every channel of every pixel. So, and it just allows much higher dynamic range, obviously. That's a great exam question. is ppm with 2 bytes per channel accumulate or better fit higher dynamic range of images comparing to the HDR format. And to ask you maybe what's the limitation of each one. And obviously, because in the exponent, you can go all the way in the exponent, all the way down to 2 to the 1 of the minus 127. Where this number comes because I'm using, if the exponent is 8 bits, then 1 bit I'm keeping for the sign, and the rest are, for the rest of the number. So it can be extremely small values or extremely large values. OK, non-local operations, already mentioned. The target intensity is not affected by the local. The target intensity might depend on the intensity of other pixels beside itself. It doesn't mean that you still need in the homework to control the alpha, beta, gamma, but you want to do something more than that. So let's just show you where it's going. What are we about to do? I'll try to pull the slides at the same time, so if you're losing me. So I have my input image, which you see over here. And I have the control and gain and everything as before. And that's the input image, very high contrast. I want to squeeze all the information as good as I can into this much narrower gap with that's the minimum intensity, that's the maximum intensity. Also look, I defined the number that I called it the local contrast. If you just look at a pixel and look very close to its neighborhood. The gap here is 1.2, by the way, between this and this, which is definitely what your eye can see. And if I just put the same gap over here, it will cause the pixels to be illuminated in different values. We had 6 values over here, 256 in your monitor. So 1.2 gap is just enough to cause it to blink slightly more. But if I'll just do, as we already discovered, if I just do linear scaling, the log domain will not save me. I'm still here where, because the gaps, the small local contrast, are also compressed by alpha, and alpha is quite tiny, now most gaps are well below 1, not guaranteed to trigger different pixels. What does it mean about how the image looks to us? It looks very blurry. Details that you saw in the original image, small parts of the tree. Let's say that you have a tree over here. I'm very good in drawing trees. Here is a tree, looks like in real life. We have high spatial frequency, quick changes between black and white. Over here, I decrease the intensity of everything over there. So even if I just show you the image scaled down, maybe you don't see the images of the tree. But why does it look to us more fuzzy? Well, because we are below the gaps that will cause the pixels to illuminate in different values. So this whole region, which are elements that are close to each other, high frequency, but the gap of the intensity after the rescaling is much smaller, they will be mapped to the same value. Result, how does it look to us? All the pixels over here are monochromatic. All the 3 pixels over here have exactly the same value. You stop noticing the details. So that is, I hope that I convinced you that fuzziness or blurriness of the image is quite related to the dynamic range. Do the compression in a less sensitive way, and it will start to look fuzzy. What can we do instead? that's in the left side of the image. And the slide describes all of it, but little. We talked about taking each pixel Let's look at the smoothing function. We had a long discussion about smoothing function, and we'll go back to talk about it in case of other applications, but we talked about it as a way for aliasing. Here it comes again. I look at the function at x, the intensity at x, the luminance at x, and I'll think about a new function s of x, where the value at this pixel x right here, x, its own value is 17. F of x is 17 in my beautiful drawing over here, but f of x minus 1 is only 1. And f of x plus 1 is also 1. What is the value of the smoothed function at x? It would be f of x plus the nearby pixels, the f of the nearby pixels, 17 plus 1, making it 19 divided by 3. So that would be, in our case, s of x is about 6.3. So it's averaged, but we mentioned it many times. It looks at an image or a signal, and it somehow smooths it, takes high point, low points, and somehow put it all in the same way. So that's what we are doing right now. You can think about different mean filters, different averaging, but there is a good chance that it will work, even if you look just, here I'm just doing average of the 5 nearby pixels. So this dotted signal is a smoothed, is the s of x. It's going somewhere, averaging the small bumps and highest point to make them all somehow on the average. I'm much more likely to be equal to the average. How else did we call it? We called it the low-pass filter. If we put it on the music, you'll hear, if you take the sound of your speaker and from your amplifier and put a low-pass filter, you'll basically hear the bass. Telling something new to anybody? You don't see something that is changing very fast. These little bumps are all but gone. Again, my overall goal is to understand what regions are more illuminated, which regions are less illuminated, but on the big scale. How do I see the high frequency? How do I see the treble for my microphone, for my sound? Help?
The original minus the low.
Exactly. So to create S, I use the convolution. If you still hate convolution, which you probably do if that's the first time that you hear about it, just think about averaging of a pixel with its nearby pixels. Now I look at the high frequency, which would be the original signal, the original value, f of x minus s of x. I removed from every pixel the value, the average value of my neighbors, basically. That's what I'm saying. I'll decrease for myself the average value of my neighbors. And of course, you can play with different, how far away pixels are still called my neighbors, but it's separated. I'll pick, what do I left with? Here are the high frequency. This is exactly h of x, h for high, is exactly the f of x minus s of x. S of x is a smoothed function that is just going all the way right here. This s of x doesn't have any bumps, any local minima and maxima, all the way from here to here. All of them have been compressed by the effect of their average pixels, of their nearby pixels, by taking the average. High of x is exactly changing very, very rapidly, but what is the amplitude? What is actually the dynamic range here, the gap between the maximum and the minimum? The contrast is very small. All the way, it's about 1.2, going from the lowest to the highest. But it changes in time very fast, very high spatial frequency. When I'm moving from x to y, asking how many minimas and maxima do I have on 1 meter of image. Very high over here, very low in this big image. Fantastic. I separated it into something that contains most of the illumination and something that contains most of the details. And the contrast is great right here. What comes next? I'm still doing alpha plus beta using the gain and the bias, but now I'm not trying to put, as usual, I'm trying to put the gain and the bias all the way into the whatever my monitor can display for the gain and the bias, but now I apply the gain and the bias only on the smooth function. In red, what you see in red, that I wrote in blue, of course, to be consistent, alpha times the smoothed function, the low frequencies, that I'm going to scale. And of course, I'll lose some details, but that's OK. It changes so dramatically from up and down that it can tolerate moving details. So if I looked at the smooth function, and let's put the gain in something closer to 1, if I put the gain at 1, then you see that the gain is very close, especially if I put the bias in the right place. The gain is very smoothed after the rescaling is very similar to the original signal. It's huge. But I can compress it. I can take much smaller alpha, take smaller and smaller alpha. Notice that the high frequencies don't change. I don't modify the high frequency, and I'll arrange it with alpha and beta so it all fits into the dynamic range of my monitor. And now it's time to remember what is my final image. My final intensity of the image would be put back, add, show, sorry. I'm not there yet. Show the corrected image with alpha and beta. Let's zoom in. In red, this is a smoothed alpha of the smoothed function plus beta. It's going all the way from up to down, but you don't have any small details. Now, what you see in magenta is alpha of s plus age plus beta. Alpha of s plus age, that's a red thing. Plus age age, the high frequencies, what I just removed at the very beginning. It was waiting for me over here. Now I subtract the smooth from the high to get, I subtract the smooth function from the original one to get the high frequencies, and I don't compress the high frequencies. The high frequencies are still quite loud. And now I add them back into the image. And here is a signal of what you got. So the dotted signal over here, and you have it also in the slides. Dotted would be alpha times smoothed of x plus beta plus age of x. The high frequencies that I generated 2 lines above. What did I get? The whole signal fits into the dynamic range of the monitor. The local gaps are more than one, so it has a good chance to trigger pixel difference after the discretization. It will look to us differently in the bottom on top of these pixels. Here is a signal after all the discretization. Let's remove some details so you'll see just a discretization. There was a gap over here. Good chance that you'll see different pixels values at the corresponding pixels. Many more details than what we had if we did not separate them. Here I just I did the same linear transformation, same value of alpha and beta to the original signal, no, without separating to high frequency and low frequency. And because I also scaled down the local gaps, the local contrast, they're extremely small. They started as gap of 1.2, but now it's 1.2 times 0.29. So they are very small, and in most cases, they don't trigger different pixels value. Here, pixels value are kept and are happy. All good. Very cool. And no AI machine learning in it all, no segmentation. It's not that I ran neural network segmentation parts that would be very hard to apply in real time that will say, oh, this is a region with high intensity, this is a region with very low intensity, so let's treat them differently. None of it. You know, take a function, take your original input, compute in addition for every pixel what is its average with its nearby, that is, decide about the kernel. If you want to do it in a better way, do it with a Gaussian something. Some kernel, if you don't want, just a box will just average between this pixel and its near neighbors. That creates for you the S, this pixel with its neighbors. Take for every pixel its own value minus the average value of the pixel with its neighbors. That determines age. Look at S, look at the maximum, minimum of S, compress them linearly. Now for S itself, the function, it is a point operation, multiply by alpha and beta. Like multiply by alpha and scale and add, delete, subtract, add beta. Linear operation, the same for all the pixels, but only in S. And add to it back at the values that you stored in age. At the values that is stored in age. See, original image with the pixels, and you have all the details that I just described. Okay, so you have it in the slides, and just S of X, you can go more fancy, less fancy about how well you're doing it. So here is a recap of everything. Here I'm doing the averaged by weighted average. What is a weighted average? I'll take the pixel myself, my own pixel. OK, let's restart for the whole slide. The input from an HDR file. Obviously, if it's not HDR files, you don't need to change anything. If it is an HDR file, then before sending it to the monitor, separate the intensity. How? Remember the formula that we had earlier that takes the red times constant plus blue times constant, yada, yada. That's the intensity. And here, black and white just describes the intensity. How do you see the intensity here? What did they do to the intensity so it will be visible at all? I had to replace it by the RGB value, usually. It is once we move to the intensity, it's nicer to work already in the log domain. And takes the intensity, and this Gaussian just says, takes the neighbors that are further away, their weight is smaller based on, put a Gaussian on you. If you don't want to mess up with the Gaussian, that's fine. Can use other masks. And at the very same time, if you want to look at what are the colors themselves, you can do. Once you remove the intensity, you can use the HSV or just, yeah. In the HSV, you can see the colors themselves, but now there is no intensity, so it looks very ugly. Separates into the large scale, that's the original image, and that's the image minus the smoothed image. What's the gaps between this and this? This is very dull, all in the same intensity pretty much. Don't see anything bright, anything glow, but you do see a lot of the small details, but the sky and the ground looks as intense to each other. No details over here, but all the small details are here. Big details you see over here. The tree appeared as one big unit. The sky appeared as one big unit. The ground appears as one big unit. Yeah, and reduce the contrast of this original image so you can fit it into the monitor. That was to take the red function and squeeze it down, but only for the large scale image, what we called S, the low pass. Add to it the details, add to it the colors, we assign the colors, and voila, you're getting a much, much nicer image. Okay, just to tell you another example. Here is a map that just showed you, the color just tells you in this original image how intense the pixel is, huge gaps in this whole part. In the church, most of the cathedral is quite dim, but there are red points, like the window that has a very high intensity. This is in watt per square radius, per meter square. What's happening? Our exercise separated the window without knowing that it's a window, without trying to change the boundary. Look at the window with all the detail by itself, and then add the window at the end as a high frequency to the church that was mostly dark, and it all works very well. Yeah. Okay, and we just repeat the same thing. It just wanted to have the slides again, how you compute the in and out. But that's it. You'll have the homework done today or tomorrow, the part about it. The grads, I'd like to have everything here, except that the filter that you're doing is slightly more sensitive. There is a very small and very easy modification. For the grads, everything else is the same. In the comments from my course previous times, people did not mention it as particularly hard. Once you understand what are the once you understand what's the average and all the strange signs of the convolution, I think that it's quite straightforward. But I'm happy to hear different opinions if you'll have differences. We can. It's supposed to be a fun course at the end of the day. Okay, questions? Thank you.